Myself, Sai Prasad, a lecturer in the Ahmedabad High School and the Junior College. Welcome to the series of the lecture of Intermediate First Year Chemistry. We have been discussing the basics of atomic structure in our last classes. That is, we have discussed the different subatomic particles, we have seen the basic Dalton's atomic theory. Today, we will start about what are the different atomic models of a particular atom, right. We know that there are few atomic models which we have a bit glance of them, that is a Thomson model, Rutherford model, Bohr's model and Bohr-Sommerfeld model, right. We have a basic knowledge about these models in our previous classes, right. Today, let us start a deep discussion about each and every model, right. As of now, here we are going to discuss about Thomson's model. Before going into that, let us recall everything whatever we have studied. That is, we have studied the three different subatomic particles, that are electron, proton and neutron, isn't it? What is the charge of an electron? We know that it is negative charge. Then what is the exact value of that charge of a electron? That is 1.6 into 10 power minus 19 coulomb. Okay. Since it is a negatively charged particle, we always place a negative sign in front of it, right. Similarly, what is the charge of a proton? The electron charge and the proton charge is always same, but since it is a positively charged particle, we have to place a positive sign in front of the value, right. What about the neutron? The neutron itself has a neutral charge, is it clear? Then next, when it comes to the mass, what is the mass of electron? It is 9.1 into 10 power minus 31 kg, which was derived from oil drop experiment, Millikan's experiment, right. Similarly, they also calculated the value of mass of proton, that is 1.672 into 10 power minus 27 kg, right. We learned that the mass of this neutron is slightly greater than that of proton, right. You can see here it is 1.672 into 10 power minus 27 and here it is 1.674 into 10 power minus 27, right. It is almost all 2 into 10 power minus 29 kind of increase from mass of proton to mass of neutron, right. When it is being converted into atomic mass unit, the mass of electron is almost all 0.00054 and mass of a proton is 1.00872 and mass of neutron is 1.0086, right. Almost these both are considered to be 1 unit, I mean 1 AMU, and electron is always considered to be as 0. Is it clear? These are the things which we discussed in our last class. Today we are going to start different models. Among them, Thomson's model was one of the basic model. When did we study about the Thomson's experiment? We studied about the Thomson experiment in discovery of electron, isn't it? Is it clear? He placed a discharge tube. After that, when it comes to a proton, when did we discuss about Thomson? We discussed in the discovery of electron and proton about Thomson and Rutherford experiment, right. After those kind of experiments, they concluded few of the things, that is Thomson's always tells that an atom is always in a spherical in shape, right. An atom is a spherical shape, right. Sphere is nothing but your ball kind of thing, and he tells that there is a positive charge is completely uniformly distributed throughout the atom, right. For example, see here, if there is a spherical atom, this whole portion except this small holes, remaining portion is completely filled with positive charge, right. And then he tells that there are electrons embedded into it. Is it clear? If there is completely positive sphere, he is telling that electrons are then and there, they are not in continuous way or they are not distributed throughout the atom, right. There are only few electrons when compared to the number of protons, right. Those are negatively charged particles. Since it is same like a watermelon, that is the whole red color part is of positive charge and those black color seeds are of electrons. He compared D.J. Thomson as watermelon model, or he also tells it as plum pudding, raisin pudding, like that, right. And one more point, he assumes that the mass is completely uniformly distributed throughout the sphere, right. What is that mass? That is nothing but our positively charged particles, right. What are his conclusions? He tells that an atom is in the form of a sphere in which the whole sphere is filled with a positively charged particles. He does not tell particle, he just tells that it is filled with a positive charge, right. And the third point is electrons are embedded into it, right, like a watermelon, right. This is what Thomson's tell, right. Is it clear? Then after that, let us go to the next model. The next model is Rutherford atomic model. We have seen the Rutherford atomic model in our different cases, such as we have seen the same contents in our 9th class, right. What was it? It is actually, it is also called as planetary model. Let us see his setup and let us discuss about his results. See here, this is a source of alpha particles. He placed a source of alpha particle and he started incidenting these source of alpha particle on a gold foil. What happens? Then he made it to transparent through this gold foil, and again the alpha particles has to incident on a, the setup itself tells that there is a source of alpha particles, right. There is an alpha particle source. From this, the electrons or this alpha particles are traveling from this point, I mean from this source, and it is getting incident on a lead plate, right. It is being passed through a lead plate, then this alpha particle ray, it goes and incidents on a thin film of gold, that is it is get incident on, this is a gold foil, which is almost all very it is completely like a thin film, right. This gold foil, after getting incident on that, what happens to this rays? We are seeing different kinds of rays. There is one ray moving this side, one ray this side, one ray this side, one ray, and again it is passing through the, I mean again it is passing through the gold foil, right. Then he made a setup of a transparent, he made a setup of a photographic plate. What kind of photographic plate which we discussed there? It is nothing but a kind of coverage on which zinc sulfate kind of things are coated, right. These are also called as fluorescent plates or photographic plate, simply we can call it as, right. What happens to this? We know that when it goes an incident on that, we can see a blind spot or we can see kind of a light on that, right. Is it clear? Then how are they getting deflected from this original path, right. That is how we can discuss here. These are rays of alpha particles, right. When this go an incident at a particular atom, he concluded that whenever these electrons are moving away from the center, then he tells that there is something in between that is moving this electron towards outside, right. Is it clear? What is that? See here, whatever it is, either it should be a positive or it should be a neutral thing, then only it has to deflect, right. If it is if it falls on the center, then it is completely deflecting back, right. Based on the, for example, if this is my atom, based on the closeness of a ray with this nucleus, the deflection angle is changing, right. If this is more closer, the deflection is very high. If this is very far, for example, if it is here, then it moves like this. If it is somewhere here, it moves a little. It is deflecting a lot, right. Finally, it deflects back in the same direction when this passes through one central of the atom, right. Then he concluded that, which means what are the major results here? He tells that most of the alpha particles which are incident on the gold foil are not deflecting, that is other than this part or other than inside things, remaining all other things are undeflected, isn't it? Then only a small fraction of angles are deflecting at different angles. Not only this, they might be deflected like, just if it is the actual angle, they might deflect like this or like this with a very minute kind of angle, right. And few of the alpha particles, that is almost the center incidenting ray, almost kind of 1 on 20,000 rays, only those are deflecting back with the same 180 degrees angle, right. What he tells? He is telling 3 points. One thing is most of the alpha particles are undeflected, and the second point is few of them are deflecting at a small angles, and only 1 out of 20,000, which is almost all less than 1% of rays are reflecting back, right. On these observations, he concluded few of the things, that is he concluded most of the atom is empty, isn't it? Most of the atom is empty, then only these rays can directly pass through them, right. Is it clear? And there are only few positively charged alpha particles, because of that only there is deflection happening, isn't it? It is not like a Thomson model, right. And he tells that there are only few positively charged particles distributed around the atom, right. Not only that, there is only 1 or 2 rays which are deflecting back, which means if there are more positively charged particles, obviously this electrons has to deflect at a very large angles, but they are deflecting at a very small angles, right. Then he concludes that there is only minute amount of positive charge present in an atom, right. What was his first postulate, I mean first observation? He tells that most of the atom is empty, and the second point he tells that there is only a minute part of positive charge present inside, and the third point he tells that according to Rutherford, according to this kind of observation, that is based on the different sizes. For example, he will take a set of angles, he will project this alpha particles in that particular angle only, right. I mean in that set only, then he can define the diameter of the atom, right. From doing such kind of experiments, he concluded that the radius of a nucleus is almost all 10 power minus 15 meters. This is radius of nucleus, and the radius of an atom radius is almost all 10 power minus 10 meters, right. This is what he observed. Based on this, he gave few postulates. What are his postulates? Based on the previous results and conclusions, he tells 3 points. What are those 3 points? Try to understand these are the major things which you have to remember. What was the first conclusion? He tells that there is only a little bit of positive charge and remaining other is empty, right. Then the first postulate relates that the positive charge and the most of the mass of an atom, like that, the positive charge and most of the region or the most of the mass of an atom is completely concentrated on a small portion of an atom. He is not telling that it is at the center, right. A small portion of an atom, that particular small portion of an atom, he defines it as nucleus, right. What is the first point? According to Rutherford, the positive charge and most of the mass of an atom is concentrated at a small region. That small region is called as nucleus, right. And one more thing he tells that this particular nucleus is surrounded by number of electrons in it, right, which are moving in a circular path. Is it clear? They move in a circular path, because he can conclude this, like for example, if there are some electrons here, based on, for example, he will be incidenting at different angle, I mean different time. For example, if this ray is getting deflected at this point, then automatically it has to get reflected at the different points. For example, if an electron is revolving around this nucleus, if I tell that there is an electron here at this instant, this will get deflected. After some time, at next instant, this electron will be somewhere here, and this will not deflect from that particular point. Is it right? That is how, by doing some trial and error methods, he could conclude that an electron revolves around the nucleus in a fixed path. He defined those paths as orbits. He defined those paths as orbits. What is the first point? He gave what is a nucleus, right. A nucleus is a specific part where the whole positive charge and whole other mass of an atom is highly concentrated at a point. That point is called as nucleus, right. And the second point is the electrons revolve around a specific path. That particular path is called as orbit, right. And one more, the third point, which is very important to understand in our future things, that is electrons and nucleus are always held by an electrostatic force of attraction, right. See here, that is we have studied a few kind of circular motion in our physics chapters, right. Based on its circular force, the force between the central atom and the revolving atom must be same, then only it stays in a circular orbit. That is why there is a kind of electrostatic force of attraction between a nucleus and the electron, right. These are the three different conclusions of Rutherford atomic model. Why this model is called as nuclear atomic model? Because in this atom he defined what is a nucleus, he discussed everything with respect to a nucleus of an atom, right. Not only that, this is also called as planetary model, just because see here there is a central element present inside and there are electrons revolving around that nucleus, right. This is similar to the same planets revolving around the sun. That is why this can also be called as planetary model, right. Now let us discuss about the defects of a Rutherford. See here, when we started discussion about Rutherford, we could find that there are few defects in Thomson's model, right. What were those defects? What did Thomson tell? Thomson tell that the whole atom consists of a positive charge, right. What did Rutherford tell from his experiment? He tells that the positive charge is not uniformly distributed, there is only a kind of positive charge at a fixed point, right, that is in a fixed place. Is it clear? He named it as a nucleus, right. A nucleus is a place where whole positive charge and the whole mass, actual mass of an atom is present except electrons. Is it right? Similarly, that will be the defect of Thomson, isn't it? And when it comes to the Rutherford, we will discuss few more defects of Rutherford. Before going into that, let us have a basic idea about what is an atomic number, what is atomic mass, right. Let us see that. What is an atomic number? Atom has to be given a particular number. What is the need of that atom? What is the need of that an atomic number? That is, see here, we are telling that there is a whole mass concentrated at a particular nucleus, right, and a whole positive charge is concentrated at that particular nucleus. Then how many protons are there in that nucleus and how many neutrons are there in that? In order to know that, an atomic number gives us a basic experimental or a theoretical value of an atom, right. For example, an atom of a hydrogen, right, hydrogen consists of one proton. How can we tell that? That is, there is only one proton in the nucleus, then we can give a number of 1. For example, if it is of sodium, sodium consists of 11 protons in a nucleus, right, then we can tell it as atomic number. Simply, an atomic number can be defined as number of protons in a nucleus, right. It is usually denoted by a symbol S, right. And we also know that an atom is always a neutral, right, an atom is always in neutral state. Is it clear? Then the number of protons is somewhere, let us say 5, right, which means it is of completely positive charge and we are telling it as neutral. Then what is the number of negatively charged particle? That is electrons, it should be 5. Is it right? Then we can describe an atomic number as not only number of protons, we can also describe it as number of electrons in an atom. Is it right? Is it clear? Now tell me, what is an atomic number? Atomic number is a number which gives the count of number of protons or number of electrons in an atom, right. And what is the one more subatomic particle left? That is neutron. Where are these lying? The proton and the neutron, they are combined together, right, in a nucleus. When the proton and nuclear are together, they are combinedly called as nucleons, right. Proton and the neutron combinedly called as nucleons, right. Then this number of nucleons, or we can directly tell it as number of protons and the number of neutrons, is collectively called as mass number, or it can also be called as atomic mass, right. Is it clear? number of protons plus number of neutrons is nothing but atomic mass. It is usually denoted by A. Is it clear? What is number of protons here? We know that this is Z, right? Let us say it as number of neutrons N. This is the relationship between atomic mass, atomic number and number of neutrons. For example, let us say a sodium has a proton value, that is Z, as 11, right, and its atomic mass is 23, atomic mass as 23. Then what about number of neutrons? Number of neutron is nothing but 23 minus 11, which is 12. Is it clear? Then only we get 23 as atomic number. Is it right? This is how the basic notations of what is an atomic number, what is a mass number, right. Then what about the different atoms? We have seen different elements, different atoms, right. We can't assure that it will have same number of neutrons or same number of protons, right. Different atoms will have different atomic numbers, different atom will have different mass numbers, right. What are they called as? How are they defined? How are they segregated? Let us see now, right. What do we call for two different atoms of having same atomic number and different mass number, and what do we call two atoms of having same mass number but different atomic number, right. See here, among them we define two things, that is isotopes. Isotopes are the two elements or the two atoms having same atomic number but different mass number. Remember, isotopes are two different atoms having same atomic number but different mass number. One of the examples is hydrogen atom. See here, where this notation is actually given by, if there is some atom A, let us assume, here it should have its atomic number at the bottom and its mass number at the top. Is it clear? That is how we describe it. You can see here the example is H11. Here number of protons or number of electrons is 1 and here it is number of mass number, right. And when it comes to deuterium, deuterium is also kind of hydrogen isotope, that is its atomic mass is again 1, atomic number is again 1 and mass number is 2, right. And when it comes to tritium, it is also one of the isotope of hydrogen whose mass number is, whose atomic number is 1 and a mass is 3, right. And one more kind of example is carbon 612, carbon 613 and carbon 614, right. These three atoms are having same atomic number, that is 6, and different mass number, right. The next is isobar. Isobar is two atoms having same mass number but different atomic numbers, right. Among them one of the example is carbon with 6 atomic number and 4 mass and nitrogen with 7 atomic number and 14 mass, right. You can get it out that why carbon will have 14 mass number, that is number of neutrons is almost 8, why not 12, right. We discussed that the carbon will have 12 atomic mass, isn't it, but from where did this 14 come? Based on the requirements and based on the position it is being placed, the atomic mass changes, right. This is what we discussed today. What did we discuss in this today's session? We started with Thomson's model, we discussed about his postulates, his conclusions, then we went till Rutherford, his postulates, and we did few definitions of isotopes, isobars, right. Let us discuss few more things about this previous concept and start Bohr's atomic model in our next session. Okay, is it clear for today? Done. Thank you.